Good evening, everyone. Good morning, Flavia.
Good morning.
Francine is here now. Boa noite, Francine. So, Flavia, thank you so much for being here with us today. It's a pleasure having you with our students in Brazil. So, guys, as I told you in our first class, Flavia is from QT, that is Queensland University of Technology in Australia. And she will be here today sharing her expertise in 3D printer and, how can I say, tissue engineering. So, Flavia, I will let you introduce yourself, okay, and your field. And when you feel ready, you can start.
Thank you, Mairim, for this opportunity to present my work. As Mairim mentioned, I work at Queensland University of Technology, and I have been working here for 9 years with the tissue engineering. And today I would like to present a scaffold guide to tissue engineering for the assessment of bone defects, reconstruction, like preclinical and clinical trials. I just would like to say that I find it easier if you ask the questions during the presentation and not at the end of the presentation. So if you have any question, please feel free to ask whenever you want. So my research focused on the in vivo and morphological and structural evaluation of 3D printed scaffolds applied to the reconstruction of critical size bone defects. And this includes the use of histology, immunohistochemistry, scanning electron microscopy, confocal laser scanning microscopy, bright field microscopes, and exact grinding systems, and also qualitative and quantitative analysis. I will give some background on why we are working with these 3D printing technologies. Bone is a well-structured tissue with a remarkable capacity of healing. However, when a defect occurs in a large quantity, your body cannot heal without clinical intervention. Currently, the gold standard of the care in the clinics is the Autologous bone graft, which is a graft that's harvested from the hip, from your own body. However, it has a limited source and donor site morbidities. As population ages and healing and bone regeneration capacity decrease, along with the limitations associated with the autograft and also the allograft grafts, tissue engineering has emerged as an alternative to overcome these constraints and these associated with these existing treatment and concepts, and also to supply the increasing need for bone graft as a material for orthopedic, oral, and maxillofacial surgeries. Our group has already completed extensive research using large and small animals using 3D printed techniques. And these techniques have been combined with autologous bone graft. So these tissue engineered techniques have been combined with autologous bone graft, bone morphogenic growth factors like BMP7, BMP2, mesenchymal stem cells, platelet-rich plasma, mesenchymal stem cells such as osteoblasts, and also a reaming irrigator aspirator, which is like technique that they use when they are reaming the femur or the tibia. So they remove these mesenchymal cells that are in the bone marrow, and then they use these cells to implant together with the scaffold. And these techniques, they are all based in the osteoconductivity, osteoinduction, and osteogenesis. So osteoconduction is the capacity of the growth of the capillaries and bone cells on the surface of the scaffold, and osteoinduction by stimulating these mesenchymal cells to develop in bone cells. So, and this leads to the osteogenesis, the new bone formation. However, novel treatment alternatives, offering off-the-shelf solutions for biomedical applications, they require rigorous preclinical and experimental evidence of clinical promise in a proxy species. Our proxy species is the sheep model. And why do we use this model is because they are very similar to human conditions. When you do the preclinical studies in small animals, they are not really translatable to clinical settings. For example, if you use rats or mice, they have a different physiology than the humans. And sheep is the most similar physiological functions to the human, hence why we use the sheep model. And the material that we use for the scaffold is mainly polycaprolactam, PCL, which is a biodegradable polyester with a low melting point around 60 degrees. And this capacity to melt enables the PCL to be 3D printed in a variety of forms, geometry, and with distinctive structural and functional properties. So this image that I am showing here is the scaffold that we mostly use in our group. As you can see, it has some geometry. For example, it has a 20 millimeter outer diameter and an inner diameter of 8 millimeter. And all this geometry is to help the cells to attach to this scaffold. So for example, if you have a scaffold that has a pore size that is too small, the cells are going to feel suffocated there and they are not going to grow. They are just going to die inside of the scaffold. So this scaffold is optimized for the cells to go there, to attach to it, and to migrate to it, differentiate, and then proliferate around the scaffold. And also the scaffold has a biomechanical property which can proportionate to the body stability, because for example, if you have like a large defect on your leg, you need to have something that is going to give you stability because you're going to walk. It cannot be so soft and it cannot be so hard as well. So it has to be optimized. So the design, as I mentioned, is to facilitate cell migration, tissue integration, promote new tissue formation, and also to have a minimal foreign body reaction. Because the foreign body reaction, I will talk a little bit more about it, but the first response of your body when you have something implanted is a foreign body reaction. Your body is going to, you put the scaffold in your body and it reacts to it because it's strange to your body. So the cells are going to attack it and are going to encapsulate it to protect your body from that foreign body that is going to be implanted there. But I will talk about it a little bit later. So 3D printing is relatively a new technique used in regenerative medicine, and it is used with the help of computer-aided design. You have a software that you put your code and you design your scaffold. It can be you can control the layering process of the scaffold. You can alter the composition time of the scaffold as well by changing the number of layers and fibers that are going to be printed. It has a high reproducibility. You can repeat as many times as you want. And it also has a commercial potential because these synthetic polymers, such as PCL, they can be used in many kind of defects, for example, bone defects, hernia defects, breast tissue reconstruction, and so on. And also it gives you the possibility of having personalized methods such as tailoring the scaffold properties according to the patient requirements. For example, if you have a bone defect that it is a 36 centimeter defect, you can print a 36 centimeter defect for that specific patient. If you have another one that has a smaller defect, like a 10 centimeter, you print another scaffold with 10 centimeter and so on. So, as I mentioned with you, we have worked with a lot of techniques, these PCL scaffolds combined with some specific surgeries. This one that I'm showing now, I worked in my PhD, and it was a membrane that was used to heal a 3 centimeter defect. And the membrane was combined with bone morphogenic growth factor, combined with a delivery system, which was an alginate to hold the bone growth factor, because as you may know, if you are going to put something in your body, for example, a localized therapy on your leg, on your tibia, for example, the growth factor, the BMP, if you put that, this is the medicine is just going to spread all over the body. You need something that is going to hold the therapy inside of the defect. So you need something that is going to hold that drug. So what we used in this system, we used alginate, so to hold the BMP inside of the scaffold. And this BMP would then stimulate bone formation, which we called osteoinduction. So this was a very thin membrane that we used. I will show in another slide the geometry of this scaffold. And this was the surgical procedure. So a 3 centimeter defect was created, and then it was stabilized with a plate, an external plate. Another difference here is that you can use external plates or you can use internal plates, which goes inside of the bone marrow. In this case, we used an external plate. And then you slid the scaffold inside of the defect, and then stabilize again, put the screws on the plate, put the alginate, and then inject the BMP inside of the defect. The time point of this study was 6 months, sorry. Another ship model that we had here was also an XL, an XL defect, which was the double of that defect, so a 6 centimeter defect. That study that I presented first has not been published yet, but this one has already been published in the Bone journal, and was a 6 centimeter defect. The scaffold again was a different scaffold, so it was an FTM scaffold, PCL TCP scaffold. So PCL was coated with a 3-calcium phosphate, which also helps the attachment of cells, bone cells, to the surface of the scaffold. However, these scaffolds, they have like limited bioactivity properties. So you need to put something else to help the cells to go inside of the scaffold. What we used in this study, we also used PRP, platelet-rich plasma, and also BMP7 to also help again to induce bone formation. Because if you put the scaffold alone, the healing is going to be delayed instead of fast healing that you would have with the help of the PRP or BMP7 or BMP2. The other study that I also worked on was the use of cortical periosteal flap, which is when they made the defect of this technique is used a lot.
Can you hear me?
Yes.
Just about when you mentioned about the therapy that is personalized. So personalized. How did you optimize this scaffold? I mean, because it's just about the size or about the layers or another thing?
Yeah, we have been doing 10 years of study on the geometry of the scaffold. So we have found out what is the best size for example, for the cells to attach to it. And so with these scaffolds, they have a specific size pore where the cells go. And for example, with the use of the BMP, the bone growth factor, you need to have something, as I said. In the first study, we used alginate to hold the drug on the scaffold. And in this study, the second study, we used PRP to also hold the growth factor inside the scaffold. But I will show later that other membrane, there are two different scaffolds. They are used a lot. The first study is a kind of is based on what is the name of the technique used in clinical settings. When you have a defect, like when you break your leg or you have a bone resection because of a tumor in clinical settings, so first they put a spacer and then they put a membrane around it to avoid soft tissue formation inside of the defect. Why do they do that? Because, for example, soft tissue, they grows faster than bone. So they put this membrane, which was the membrane that I used, and then they put some resin inside. Once this membrane is there and you have like some soft tissue around it, they remove the resin that they put inside, and then they put the autograft inside of the scaffold. So all this membrane or the scaffold, they are optimized. So you have cells going there to grow. I don't know if I answered your question, but
Yeah, I got it. And Saulo is asking if the scaffold is extruder to, yes, Saulo, as I mentioned in our first class, is correct your question. And how long is your Flavia? How long is your model? Like how many? It's 3 months, like hernia or not?
so these the cortical periostal flap, it was 12 months. The first study that I showed was 6 months.
12?
12 months. This one, the cortical periostal flap, 12 months. The first one was 6 months, and the second one was 12 months as well.
Oh God, it's a long time. Okay.
Yeah. I will talk a little bit later how we follow the healing response during this time.
And Flavia, Carla is asking if is the scaffold absorbed?
Yes.
Maybe 2 years later?
Yeah, it has around 24 months. It not completely, but most of the scaffold is reserved. So the cells go there and then they start to grow, and then mainly the scaffold will be like to give you stability as well, because as I said, when you have like loss of bone, you cannot walk, right? You have like a gap between two parts of the bone. So you need to put something that is going to hold that defect and then is slowly degrading. So it is giving you stability and also the time for the cells to grow there and create new tissue, and then having like a functional healing. Because you can have the healing but not be functional, right? The functional, when we say functional, is about the stability that is going to give to you. And as I said, the first thing that's going to happen is the formation of soft tissue, because these cells, soft tissue cells, they develop faster than bone. So if you don't put anything there to avoid these soft tissue, the tissue cells to grow there, your defect is going to be filled with soft tissue and not bone. So you don't have a functional healing because soft tissue is not stable. So you cannot walk properly again, ever again.
And Flavia, one more question. As you said, the PCL could be rejected, okay?
Yes.
So, do you there are some do you know how the percentage about the rejecting, or it's hard to say?
I don't know the percentage of PCL scaffold because the PCL, this PCL that we use is a medical grade, and we have never had any cases of rejection in here, but this is with bone, right? And we have been studying the properties of this scaffold for 10 years, but it is quite well accepted by the body. So, but for example, when you work with other polymers, like we saw with the study that we did together here, Marin, for the hernia studies. For example, they used the what was the name of that mesh?
PCL as well.
Was PCL, but
propylene.
yes, and yeah, we used the PCL and then we compared with the polypropylene.
Propylene, yeah.
So that kind of mesh is made to induce the body to encapsulate it, right? Because it's like when you have a silicone implant, you put the silicone on your breast, and then what happens, the silicone is encapsulated and then it stays there, right? So with the pop, it is a similar situation. It's going to cause a foreign body reaction, and the mesh is going to be encapsulated, and then that mesh stays there forever, holding your tummy, or for example, in the case of vaginal prolapse or abdominal prolapse, the mesh stays there forever, and the patient can feel it, and is not degradable. Sorry, I think I
it's a lot of questions now.
A bit lost on the.
And today they are really shy, and I think they. Oh my God, 3 questions. Saulo, I think it's correct, your question. Did you see the questions, Flavia?
I'm looking at it now. As ovelhas são tratadas com algum imunossupressor, corticoide. No, they are not treated with immunosuppressor. So what happens is, because as I mentioned, we have not had like these cases of rejection because the PCL that we use is a medical grade. So it's a special kind of PCL, because you can buy PCL from other companies like Sigma but they are not medical grade. So they are made that so they don't cause like an infection or an inflammation.
And
Saulo fez uma pergunta.
Saulo, I answered it already, but now, oh my God, I don't know the order anymore. You can see and the answer, Flavia. Gladson, is the therapy for all types of bones or only long bones?
Long bones. We have tried 2 centimeters, 3 centimeters, 6 centimeters. I'll show in one of my last slides the clinical cases, but we have been using in mainly for large bone defects. Why large bone defects? Because you would use the scaffold for a critical size defect. Why? Because, for example, less than 3 centimeters, your body can heal that defect. Your body has the capacity to healing of healing, between 2 and 3 centimeters. So you would not need a scaffold to heal that defect. You would use the scaffold only when you have like a critical sized bone defect, which is a long defect, more than 3 centimeters, because then you need help for healing, because your body by itself cannot heal it. So you would put a scaffold, so then it would heal. Hence why we use mainly for long bone defects, and you don't use it in clinical settings. You would not use a scaffold with less than 3 centimeters. You don't need a scaffold because your body is going to heal. Eu não entendi essa pergunta. Sim, como uma prótese...
Não. É que eu respondi para o Saulo.
Okay.
Saulo answer and did the question and I answer. And the Gladson is asking another thing as well.
And is the medullary bone normally regenerated? Okay, so when we have the time points, right? So you have like a bone process that is going to happen when you start with the scaffold, right? So in the beginning, I have another slide talking about this bone process, right? You would have first a blood clot is going to form. And then in this blood clot, you would have cells that are going to initiate the healing. And then a cartilage scaffold is going to be healed. And then this cartilage is going to mineralize and then become woven bone. Woven bone is a kind of bone that has less mineralization. And then this woven bone is going to remodel to become bone. So in this process, that from woven bone to bone, mineralized bone, the medullary canal is going to be formed because there is a remodeling process that the cortical bone is going to be formed, and then the medullary canal is going to be formed again. So first, you would have woven bone everywhere, even in the medullary canal, and then later on, with the remodeling, then cortical bone is going to be formed in the outside, and then you would have the space of the medullary canal formed later. I will show you histology image of it soon. So I'll keep going with this because I am in the first ones still.
Okay, so, and Fernanda has a question. Just more, Fernanda, now you can.
Just one question. You said there is some case that a plate has to go with the scaffold. So the scaffold doesn't replace the plate or screws, but it has to be together?
So you see in this image here, can you see the plate on figure E?
Yes.
So this is the plate, and it's an external plate. In the middle here we have the scaffold, okay? With this, in this case of this cortical periostal flap, the scaffold was cut in half because this cortical periostal flap, which was a bone flap, like a piece of bone, was put inside of the scaffold with some vascularization, like some veins inside of it to help with the healing. So that's why it was cut in half. Normally it's not cut in half. So they close that scaffold, and then they stabilize the defect with the plate. So it's externally fixed. You have the scaffold here. Sorry, are you seeing this? My cursor, my arrow?
Yes.
So we would have the external plate on the outside, some screws goes and then under the gap, which is here, and then on the top of the gap in here. And then the scaffold is here. So after 12 months or 6 months, this is going to be healed, partially healed. And then this plate is going to be removed. It doesn't affect that gap So bone is going to be formed there. So you remove the screws that are on the top and on the body, and then you analyze the healing. Did I answer your question?
Yes, yes. So the scaffold is to accelerate the healing.
To help with the healing, not really accelerate is to help and also to give stability to your defect, right?
Okay.
So it's to induce bone formation as well. Induced, conduct, and then regenerate new bone.
Okay, thanks.
Okay. So in this cortical periosteal flap, what we used is, so in figure A, we are showing how we harvested the flap. So this, on figure B, you can see flap there, right? This is the flap, so it's a little bit a piece of bone. And then you have the vascularization connected with this flap. So this piece of tissue is alive. And then they inverted the flap. So they hold it so it would fit inside of the scaffold. The scaffold was then divided in two halves, and the flap was inverted and placed inside of the defect, and with this vein connected to it. After that, the defect was stabilized with plate, and the defect was closed. And this was the time point of this study was 12 months. Today I talked with Mairim, and I said I wanted to focus on the bone defects because this was studies that we have been doing in the last 10 years, and it led to the establishment of our sheep model, and it was published in the Nature Protocols. And I will just talk a little bit of the main stages of how to do this research and how to achieve the same results that we had achieved. So as I mentioned in the beginning, why do we use the sheep model? Because it is the most suitable large animal model recapitulating human load-bearing conditions, and it is a major requirement for scaffold translation into clinical settings. Why this load-bearing? For example, if you are working with rats or mice or any kind of rodent, is different because, as you know, they have 4 legs and we have 2 legs, and also the size of them. The load-bearing conditions that I am talking about is that, so when they are walking, they don't have too much load. So the healing is different when you have a lot of load and when you have little load. So, and the sheep, they are bigger animals, and they are very similar to human conditions. And also the other very important point that we need to make here is that when these sheep that we used for our research, they need to be 7 years old, because when they get to this age, they have osteon formation, which is the main structure that is going to be formed for bone. And it is the same structure that humans have. So you can follow the cellular regeneration process through histology, which would be very similar to humans. This preclinical model, it follows 4 stages, which is the pre-operative planning and preparation, and also the operative procedure and the post-operative management, where the sheep are going to be kept, if they are going to use steelings, so they would not be having too much load, and also with the post hoc analysis. How do we analyze these defects after the time point has been achieved? So first is when the time point is done, like 12 months, 6 months, we remove the defect with the plate and everything. So as you can see here, this is a tibia. So you have this is the entire leg, and then you would do the mechanical testing and test for torque and for stiffness of the mechanical stability of the defect. So you would like the torque is like to rotate the bone, so you know what's the strength, in which strength they will break, and also the stiffness would be how stiff that bone is. And also during the study, we also follow the healing, monitor the healing through X-rays. So at 4 weeks, at 1 month, 2 months, 3 months, 6 months, 9 months, 12 months. So we can see how the healing is progressing. And after we remove the defects and we start to process it for histology analysis. And the first step is to fix it and then do the micro CT of the samples. So the microcomputed tomography of the samples to analyze for the macro geometry of the defect, and also to analyze the bone volume. So to check how much bone was created during that study. And then, as I mentioned with you, in the bone follows like a repair process. So first you have a blood clot with a lot of immune cells are going to accumulate there. And then these cells also include inflammatory cells that are very important for the healing. So these inflammatory cells, they are mediators of mesenchymal cells. These mesenchymal cells, as you know, they can become bone, they can become soft tissue. So they are important for the healing. So mesenchymal cells, they are going to differentiate to osteogenic cells, so bone cells, and they are going to create a soft callus, which is composed of cartilage. Cartilage is a more soft tissue than bone. So it creates like a template where the cells are going to grow on it. And also these templates are going to be invaded by are going to be vascularized again, and these vascularized cells that are related to this vascularized invasion, they are going to form new bone. As I said, the new bone that is going to be created in the beginning is a much less functional bone, which is called woven bone. It is less hard. It is a bone that has not an organized structure yet. It is going to be organized later through the remodeling process, where the medullary cavity is going to be created again. But how do we analyze this process? We use histology to analyze this process. So we have, first we monitor through the x-rays, we do the mechanical testing, micro CT, and then we do the histological analysis. We can use two models of analysis, which is with resin embedding or paraffin embedding. For resin embedding, we use like specific staining, such as Goldner's trichrome, Movat's Vancosa Picrosidus red, which is a fluorescent staining that is going to give you the structure of the new collagen fibers that are going to be created, and also paraffin samples that we use H&E, mesentrichrome, similar stainings that are going to show you the structures that are going to be formed. Because we wanted to know, so here is the defect, a 3 centimeter defect, and we want to know how it is, the healing, it is progressing, right? So what we do, we explant also part of the host tissue, part of the bone, the sheep bone, not the one that is being regenerated, but also the one that it is there, the two ends, parts of the two ends that are already there. So we have like a little bit of host bone, and then the new bone formed, and then host bone here in the distal part. So you want to know the interaction of the host bone with the new bone formed, and at the distal and proximal part because they behave differently, right? So the proximal part, it is closer to the upper body, and the distal part, it is further to the body. So you have more mechanical loading on the proximal part and less mechanical loading on the distal part. So you want to know what is happening in all of these areas. What is the contribution of these endosteal cells that we call to the new bone that is being formed, and also the contribution of the new tissue that it is created around the scaffold, which we called periosteal cells, because the soft tissue that it is created around the scaffold is called periosteum, so periosteal cells. So I usually also analyze these cells through scanning electron microscopy. So I do some kind of etching where I expose the cells, and then I can see the bone cells here in green, and also the blood vessels here in red, and also my scaffold in blue here. In this case, it was the membrane that I used that had very small fibers. And here I'm showing the interaction of the blood vessel with the scaffold and also with the bone cells. Can you see that the geometry of the scaffold is very similar with the size of the, it's very similar to the size of the scaffold, that the cells, maybe here they are confused and they are thinking that this fiber is a blood vessel, so they are attaching to it. Of course, the scaffold, it has also some coating, 3-calcium phosphates, with the cells, they like it because it induces bone formation. So it's like attractive to the cells to go there because it has the resource that they want to grow. Yeah, and then a lot of cells that are involved in this process, not only the bone cells, but also a lot of macrophages in case of the, we were talking before about foreign body reaction. And they play a pivot role in bone repair. So we have two kinds of inflammatory cells, which we call M1 and M2 macrophages. And M1 is very important for the initial healing of the defect, because they are going to promote an inflammatory reaction, promotes the initial inflammatory response to clear the damaged tissue and to induce osteoclastogenesis. So in the beginning, you need these immune cells to go to your defect site. So they are going to try to clean the area and then to also differentiate into new bone cells. And then the M2 macrophage, they are called pro-healing macrophages because they promote tissue healing and regeneration by assisting the tissue remodeling and also the inhibition of inflammation. So they are going to help with the tissue formation, and then also to inhibit the inflammation processes. But mainly they will help with the neovascularization, the stimulation of collagen and fibroblasts, the scaffold integration, and excuse me, and support all stages of bone regeneration. And why is it important? So when Mairim was here, we worked on the hernia defects, and we used a PCL scaffold and a polypropylene mesh, which is used in clinical settings. So this is the PCL, and the second one, figure D, is the mesh that is used in clinical settings. So here with the scanning electron microscopy analysis, you can see the difference of these cells. This figure A is the propylene mesh, which is like a thread, like a rope. It's very stiff, and you can see the size of the pore size of this mesh. And figure B is the scaffold, the PCL scaffold. You can see that it has a smaller pore size, and also the size of the fibers are very different. So the polypropylene has a much larger fiber, and the PCL has a much smaller fiber size. So this is very important, this geometry, because, for example, think about the cells going into this mesh, and think about the cells going into this scaffold, this PCL scaffold. This has a lot of space. So the cell would get lost here. There is nothing to attach to stay there. So here you would have like less space. The cell would have a lot of space to grow to, and here not so much. That's why the first the first reaction is really important, because here with the polypropylene, the cells are not going to grow a lot because there is nothing to attach to it. So your body would encapsulate it because it's going to stay there, it's going to cause the first inflammation, and the inflammation is not going to resolve. So the other studies that we also work here is the breast scaffolds, so that we have been working on lately. And the model that we use is the pig model. So this is the scaffold that we currently are printing and we are studying, but this is in the very beginning of the study. And we have already published the technique that we have been using to study these breast scaffolds. And here I'm showing where the scaffold is implanted. So this blue part here is the scaffold, and here the geometry of the scaffold that we have been using. So as I said, one very important thing is the foreign body reaction that these scaffolds are going to cause in your body. This foreign body reaction can lead to an inflammation that can stay there forever and cause an infection, and then the scaffold is going to be encapsulated, and this capsules is going to form like a biofilm around it. And then this biofilm would cause a rejection of the scaffold because, as you may know, the biofilm is really hard to penetrate, for the cells to penetrate inside of the biofilm, because you encapsulate it and then you have another layer of film that is going to encapsulate it, and it's going to be closed. So Mairim and I, we published a study as well for a patent review on the antibiofilm fungal drugs, that we talk about the formation of these biofilms. And also in our group, we have a girl that she is working on the coating these scaffolds with antibacterial albumin and tannic acid to reduce this rejection and biofilm formation for breast reconstruction. So what she could find is that when she coated the scaffolds with human serum albumin, if you see picture A and B are the scaffolds uncoated, and you have a lot of bacteria in it, and figures C and D is the scaffold coated with human serum albumin, and then you can see that there is much less bacteria on it. And figure E is the scaffold coated with human serum albumin plus tannic acid, cross-linked with tannic acid. So it even improved even further the antibacterial activity of this scaffold. You can see that there is some differences, much less cell bacteria on the structure, on the scaffold structure, and also that showed morphological change on the bacterial membrane, suggesting that the possibility of membrane disruption, which is really good. As I said, the biofilm creates like a membrane that is very hard to penetrate. and she could have, and with this coating, she would find that it is possible to penetrate this membrane. Yeah. And this, I'm showing the illustration of, so we are already in clinical trials. So these phone scaffolds that we are using, they are being translated to clinical settings. And I think Renata would like to ask something.
Yeah, I have it out. Once you have infection, bacterial infection with biofilm, how can you take the scaffold off? For example, if you have a biofilm with a breast prosthesis, you can take the prosthesis off.
You have to remove.
Yeah,
You have
remove.
to
Can we do it?
remove the entire prosthesis.
Yeah,
and then you need to treat the area with antibacterial and make it clean again, so then you could implant something else again.
Yeah, so can we do the same with the scaffold? Because I think that it's I always think that the scaffold is like penetrating the body. So
yeah, you would have to remove the entire scaffold. You wouldn't leave the scaffold there because it is already contaminated. So you would have to implant a new scaffold again, and then start the entire procedure again. And that's what they do, for example, when you have like infections with large bone defects in clinical settings. They clean the area again, they treat the defect with antibiotics, and then they just go there again to try another surgery when it's clean and healed. That's why it takes very long time when they have like these inflammations or contaminations to heal a bone defect. It takes like years.
but
Yeah,
is it possible
you would
to
have to remove it.
lose? Yeah, I
Say
know,
again.
but is it possible to lose? Is it possible to lose some part of the scaffold? I mean, is it possible the scaffold be broken inside the body?
Yes, but when you use the X-rays, right, to analyze your defect, you would know where the scaffold is. It is not completely degraded yet. So these kind of inflammations you would have, or you could have in the late process, but also mainly they occur in the beginning of the implantation. Okay. So I'm showing here we have treated a patient with had like a 36 centimeter defect with an optimized scaffold. So you can see here that he had an osteomyelitis problem, and then he had an infection, and then he lost almost his entire tibia. So here you can see the gap of it. And then the scaffold was 3D printed and personalized to his defect. And then it was implanted on his leg. And then we used the plastic surgery in conjunction with a plastic surgery, right, where you would have also the help of the vascularization of his own body, because the main problem with the scaffold is to get the scaffold vascularized, so the cells would go into the scaffold through vascularization, right? So with this technique, the cortical periosteal flap, you would have vascularization inside of the defect, which would help for the healing. So, and yeah, so this was already translated into clinical settings to a 36 centimeter defect. The patient, it was like 4 years ago, the patient is walking again and have a functional leg again, which is really good, very promising. And here I'm showing some clinical case where we have also used our scaffold. So that tibial defect that I just showed, also in the skull, where this guy, he had like an accident, a motor accident, and he lost part of his skull. And another tibia defect and a femur defect. And this is a girl, she had like deformity of her pectus, and then a scaffold was used to give her the form again of the pectus, as you can see in the first before and after surgeries. So yeah, that's what I have been doing here for 9 years. Thank you.
Thank you, Flavia. It was amazing.
Thank you, Mairim.
André, huh?
I'll just stop presenting so then I can look at the camera.
No, you can. I didn't see if you answered already, Luis André, about the number of examples.
Number of experimental per group, right? And usually we have like the experimental group, 10 ships, and then we have 10 ship, and then we have the control group, which is also 10 ship, and then we also have the positive control group and the negative control group, which would be like an empty defect, and the positive control group would be like some kind of techniques that are being used in clinical settings, right? So, but usually with sheep, we would use 10. And sheep is, you have to have in mind that sheep is a very expensive animal to treat and to maintain. So we would love to work with a bigger number, but this would be like impossible. It's too expensive.
Now they have a lot of questions. Again, can you see Saulo question?
Thank you, Saulo. Commercialization of this technology. It is, we have a patent of this scaffold, and it is already being commercialized. So Osteopore, my boss here, he has this patent on this scaffold, and it is printed by Osteopore. So, but really commercialized, I'm not sure what he means by commercialized. If it is in the market, if you could buy from the shelf, not really. No, you would have to order like a scaffold, to a specific scaffold, and then they would print for you. But we have a patent on this scaffold. I don't have, so my boss has.
Dietmar, they know Dietmar. I
Yeah.
sent him then a video. Flavia, before I forget, can you put in your first slide the presentation title for me? Take a print screen.
This one. So, Mairim, some of the images that I presented here have not been published yet. So if you only the image that journal next tweet, that's okay to take a picture of it. But the other ones that they have not journal next tweets, they have not been published. And can you keep it confidential, please? So not to share with everyone.
I can't share the video.
That's okay. You can share the video, but just
the pictures. Flavia,
you can share it. I'll explain to you later.
Okay. Can you close this page in your presentation? Okay.
And the presentation?
No, put the presentation and smile. Where is your presentation?
My presentation is here. This, right?
Yes. No. Okay. No. Again.
Sorry, my computer is
Okay.
it's too much.
Smile, please. Please smile for me. Okay, I got it. Okay, guys, we have more questions. You can close the presentation, Flavia. Thank you.
Thank you so much for this opportunity, Mairim, and we keep in touch. Thank you, everybody.
Always, always. I think they don't have more questions. It was really good talk, Flavia. Again,
Thank you
always.
so much. Thank you. Bye-bye.
Okay. Bye. Have a good day, Flavia. Good night, everyone. Bye.
Bye, good night.
Bye, thank you.
Bye, thank you. Good night.
Thank you. Bye-bye. Oka.